This video is going to show you how to use ideas around vectors and momentum to work out what happens when two objects collide that aren't head-on. These two objects can be described as colliding head-on because the direction of movement with the black arrow is exactly on top of a line joining up the two centres of masses. And of course very few collisions are really like that. Most of them are like this, and here you can see that the centre of masses are not lined up along the direction of travel. What do you do now? Because of the non-straight-on nature of this collision, our two balls P and Q are going to move off in different directions, as you can see. So this is a much more realistic collision. Let's label up the starting conditions. We'll say that P moves with a velocity of u meters per second towards stationary Q. We'll let P then move off at V, which you can see is clearly different to u, and Q moves off with velocity W. Yeah, lots of letters here. We'll let the angle between the straight on position here and the velocity v be theta. Now if we dot back our two vectors for v and w, you can see those with the black lines there. They create a right angle. Now that's not always the case, but that's the one we're going to work with this time. In situations like this, it can be very helpful to work with momentum. And in order to do that, I'm going to assume that both balls are the same and that they have a mass m. The wonderful thing about momentum, of course, is that it is conserved in collisions. But more interestingly for us is that we can consider the x and y components of momentum separately, and the same rule applies. So all the components of momentum in the x direction are the same before and after the collision. And of course the same is true for the y direction. We'll begin by considering the momentum in the x direction before the collision. Well, that's just going to be p in the x direction, and it's going to be equal to m times u, because Q is stationary. Now when we're dealing with the after situation, we need to consider the contribution of momentum in the x direction from each ball. So let's start with P. Now P is moving like this with a velocity v, and there's an angle to the horizontal of theta. Now we need to find the vertical component, what we could call Vx, I guess, and hopefully you can remember from your trig that that is simply going to be V cosine theta. Now let's move on and consider the ball Q, which is moving like this with velocity W. Just like before, we're interested in Wx. I'm going to draw the whole triangle out this time though. What's this angle? Well, that angle there is going to be 90 minus theta, and that's because here we have a right angle. That means that this angle here is going to be theta. Therefore, the easiest way to think about Wx is just to use sine instead of cosine. So the component Wx is going to be W sine theta. Now we can easily work out the momentums. So the total momentum after the collision is going to be the component from x, which is going to be mv cosine theta, added to the component from q, which is going to be w times m sine theta, and the whole jolly lot is equal to mu from our starting position. And now we can simply disappear the m's, and so we're left with a situation like the starting velocity is equal to v cos theta plus w sine theta. Now we're going to move on to the y momentum, py. In the initial condition, there is no component of velocity in the y direction because it's moving perfectly along the x-axis. Therefore, there's no component of velocity in the y, therefore the initial momentum is a big fat zero. Now, just like before, we need to consider the two momentums for v and w independently first. So here's the triangle for v. We're interested in this component here. We know that angle is theta. So v in the y direction is simply going to be v, the hypotenuse, times the sine of theta. Now let's do the same thing for w. W we know is coming down like this, and as we saw last time, this angle here is theta, and we actually want that side, which we're going to call wy. This is w, therefore wy in this case is w cosine theta. It's important now to be aware that the momentum of ball P is in the upwards direction, but the momentum of ball Q is obviously in the downward direction. 180 degrees difference, one is positive, the other is negative. So let's round up now. The original momentum was 0, meaning that the sum of the final momentums must also be. So that means that m times v sine theta, the momentum of ball P, added to the momentum of ball W, which is negative mw cosine theta. Now we can rearrange this to get us that mw cosine theta equals mv sine theta. And of course our m's will cancel out. For this last section, we're simply going to take the three vectors for velocity out of this diagram and draw them like this. Now it's a truism to say that in physics the final momentum must equal the initial momentum. So I'm going to take the two red vectors out, which represent v and w, and put them tip to tail like this. Now this vector over here, this black one, is our initial momentum, and if we join the two ends of v and w together, that vector there represents the final momentum, and they should be equal, but you can quite clearly see that they're not. PF has a vertical component, PI doesn't, therefore they're not the same. So probably what's happening here is that the diagram that I've created isn't to scale and is actually representing an impossible situation. Along with that, we do know that this is a right angle and that this final momentum here is made up of the momentum of the ball P, which is mv, and the momentum of the ball Q, which is mw. And of course the initial momentum over here was just going to be mu, which should be the same as this one. So we can also write mu there. Well, now we've got a right angled triangle, which means of course that mu all squared equals mv all squared plus mw all squared. So what this is going to leave us with is u squared equals v squared plus w squared. We should just end up here by saying that it's a well-established thing in physics that if you have two masses that collide along a line which isn't along the centre of masses, then you get in fact a right angle, but the two velocities don't have to be equal.